determine whether a molecule is polar or nonpolar is really helpful in a lot of applications in chemistry, like figuring out whether something's soluble or not. Often, if you know whether it's polar or nonpolar, and you know whether what you're trying to dissolve it in is polar or nonpolar, you can figure that out pretty quickly. In order to figure out whether something's polar or nonpolar, you need to be able to do a Lewis dot structure. So if you haven't watched the video on that yet, start there, and then come back and watch this one. The real question when we're talking about whether we have a polar or nonpolar bond is whether electrons are shared equally. So in a polar bond, you don't have equal sharing. So this is not equal sharing of electrons. And in a nonpolar bond, it's like BFS, total equal sharing of electrons. The electronegativity of the atoms that are involved in that bond are going to influence whether the bond is polar or not. So electronegativity is kind of like an atom's muscles. So you can think about your atom as having big muscles. Whoa, those are some super big muscles. There are his little tiny hands. And if the atom has really big muscles, then it has a really large electronegativity. I would not want to be in a tug of war with that atom. Versus his buddy over here, who's really small and just has wimpy arms and hands. Can you tell I didn't take any art classes? I did take West African dance, though. There's my wimpy atom. And if these guys were going to duke it out over a pair of electrons, who do you think would win? Well, the one with the big muscles, or the big electronegativities. So, atoms with large electronegativities are able to attract those shared electrons towards themselves. The electronegativity increases across the row of the periodic table and up a column. So that means our most electronegative elements are found in the upper right of the periodic table, and our least electronegative are found in the lower left. As you can see from our table of electronegativities, here's fluorine, really, really high electronegativity. Here's cesium, really, really small electronegativity. Students want to know often whether they have to memorize this table, which always kind of makes me laugh, but not really. No, you do not have to memorize this table. If I wanted you to use it for an assessment in class, I would provide it for you. In general, what I'm going to expect is that you know those periodic trends. That if you didn't have access to this table, but you did have access to a regular periodic table, you would know that as you go up a column, the electronegativities increase, and that as you go across a row, the electronegativities increase. So if I handed you a regular periodic table and asked you who was more electronegative, nitrogen or fluorine, you could tell me because nitrogen and fluorine are in the same row of the periodic table, and fluorine is farther over to the right. The place where you might find yourself needing to use this would be a homework problem, where you're asked to calculate the specific electronegativity difference between two atoms in a particular bond. So, polar bonds, or nonpolar bonds, really. In a nonpolar bond, the bond that's formed between the two atoms, those atoms have the same or very similar electronegativities, and so there's equal sharing. So it's kind of like, here's my atom, here's my other atom, there are my electrons in the middle, and they're precisely in the middle because, hey, we like each other, and we share equally. In general, that's going to be bonds of the type where we have X bonded to X. So something bonded to exactly the same something. Except for one instance, and that is the carbon-hydrogen bond. You want to remember that because it crops up fairly regularly as a nonpolar bond that students don't remember, so you want to be aware of it. In general, if you have a bond formed between two different elements, except for carbon and hydrogen, then we've got a polar bond because you don't have the same electronegativities, and somebody is going to be able to attract those electrons closer, which means that somebody else is going to be building up a partial positive charge, and we're going to start to see a partial negative over here. These little squiggly things I'm drawing here, this is a lowercase delta, and it pretty much means partial. We can check out the electron distribution of some different molecules here. Here we've got F2, and you can see all the electrons are shared equally, everybody's happy, it's very symmetrical. We look at HF, where fluorine is very electronegative and hydrogen is sort of a medium electronegativity, and we see, we're moving electron density away from the hydrogen side, and it's a lot more over here on the fluorine side. If we go all the way to lithium fluoride, which is an ionic compound, where we've got lithium ion and fluorine ion, now you've got lots of electrons hanging out over here because they went to fluorine, and not as many over here because lithium lost its valence electron to give to fluorine. There are some specific ranges that will help you decide whether a bond is polar or nonpolar or ionic. I'm providing these more as a reference tool than as something that I want you to memorize the specifics of. So if you run across a homework problem that says the electronegativity difference of these two atoms is 1.3, you could say, oh, I know I need to consult that table. And here's 1.3, it's polar covalent, there's unequal sharing of electrons. On an exam or quiz in class, I'm not expecting that you've memorized this. So I'll be expecting that you remember, hey, X bonded to X is nonpolar, and X bonded to Y is generally polar, unless it's CH, in which case then CH is nonpolar. How can you predict the polarity of a molecule? Up to this point, we've been talking about predicting the polarity of a specific bond, but now we're saying, hey, if I have this molecule, tell me about the molecule as a whole. I can tell you that this is a nonpolar bond, and this is a nonpolar bond, and this is a nonpolar bond, but tell me about the entire molecule. Is it polar or nonpolar? Well, in order to figure that out, you have to draw a Lewis dot structure, and you need to check the arrangement of the atoms and the bonds and the non-bonding electrons. Because symmetrical molecules will be nonpolar, while asymmetrical or non-symmetrical molecules will be polar. For example, let's redraw that molecule I just put up there. And we see I've got hydrogen, 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 but hey, this is not a hydrogen. So therefore, I don't have a symmetrical molecule. I don't have all the same things attached to my central atom. And because that's the case, this would be considered a polar molecule. If, on the other hand, I had carbon attached to chlorine, and chlorine, and chlorine, and chlorine, everybody is all the same attached to my central atom, so this would be a nonpolar molecule. It's symmetrical. Here are some examples to look at more closely. Let's take a look at this one in the corner here. This NH3 molecule actually has a non-bonding pair of electrons sitting on that nitrogen, which the picture doesn't show. But I want to point that out because anything that has a non-bonding pair of electrons on the central atom is automatically going to be a not symmetrical molecule. Because if you look here, you've got hydrogen, 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 whoops, not hydrogen. So trigonal pyramidal shapes, whoops, didn't spell pyramidal right, pyramidal, and angular shapes, these will always be polar molecules. So, are the following compounds polar or nonpolar? Take a moment, stop the video, draw the Lewis dot structure, decide for yourself whether they are or they aren't, and then start it back up and listen to the answer. So, carbon dioxide, carbon bonded to two oxygens, got some electrons, got some electrons. We look at this and we see same, no non-bonding pairs of electrons. So this is a symmetrical molecule, this is nonpolar. H2SE, SE, some non-bonding pairs of electrons, some H's. This one's a little bit tricky because it looks symmetrical, but what we want to remember is that this is actually a molecule in three-dimensional space. And that means that my H's are not actually lined up like that, and my non-bonding electrons kind of going out here. So it looks symmetrical the way I drew it over here, but in reality it's not. And what can be helpful here is to recognize that the shape of this molecule is bent. And it's not symmetrical because I don't have exactly the same thing all the way around, so this is a polar molecule. CHF3, got my H and 3 Fs. And you can see fluorine, 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 not fluorine, so not a symmetrical molecule, so this is polar.